Honors Pre-Calculus Final Exam Review. This is going to be number 60 for 2013. And this says to verify that each equation is an identity. So one important thing I want to emphasize when we are verifying an identity is that we are not looking for an answer. What we're looking for is a process that shows that this is true. This is already being stated as true. So what's important is that we are showing a process of reasoning that proves that it's true. So we're not looking for an answer, we're looking for process. That means we must write clearly, we must show every step. We always would want to do that anyway, but especially in this problem, there's no answer to get. It's all about showing a process and showing your reasoning. So on number 60, it's a little unclearly written here because this exponent is a little odd, but what that means is 1 minus cosine x times 1 plus cosine x equals sine squared x. So probably what I would want to do here is FOIL this out. So when we see a product of two binomials, we're going to FOIL them. So we're going to go this times this, this times this, this times this, this times this, causing a little bit of an earthquake there, but that's how that should look. All right, so when I FOIL that out, I get 1 and then plus cosine x, then minus cosine x, then minus, when I do cosine x times cosine x, it should be cosine squared x, and that equals sine squared x. Then I'm going to notice that these middle terms cancel, plus cosine x minus cosine x cancel out. So now I have 1 minus cosine squared x equals sine squared x. And by the way, it's completely legitimate to jump from this line immediately to here because you know that when you multiply a product of binomials like this, you get a difference of squares. So you don't have to show this step as long as you confidently know that this product is equal to 1 minus cosine squared. Now you're just going to take advantage of one of your Pythagorean identities. I'm going to write some work off to the side that's not critical for us to show, but to just show how I'm going to justify this step. I know that sine squared plus cosine squared equals 1. That is the most fundamental of all trigonometric identities, and it comes from Pythagoras' theorem being applied to the unit circle. Interesting, a Pythagoras theorem, a theorem about right triangles applied to the unit circle yields such a powerful result. Now, I'm interested in this 1 minus cosine squared, so what I could do is subtract cosine squared from both sides. So minus cosine squared, and my result is sine squared x equals 1 minus cosine squared x. So because of this form of the Pythagorean identity, got Pythagoras' name on it, but he didn't invent it. Because of this, I can replace the 1 minus cosine squared with the sine squared. So then I can say here, sine squared x equals sine squared x. And this is what the end of my identity should look like. My identity proof is that I started with something that we're claiming is true, but it's not obvious that it's true. I do some algebraic steps and some identities, and I come up with something that is obviously true. Sine squared x equals sine squared x. This is called the reflexive property of equality, that something is equal to itself. It's the most fundamental meaning of identity. All right, so I've taken advantage of this Pythagorean identity. A nice thing to know is that you could also subtract the sine squared from both sides. So we have another form of this fundamental Pythagorean identity, cosine squared x equals 1 minus sine squared x. So as we're doing our identity work, we always want to be watching for if I see 1 minus cosine squared, I'm immediately going to replace that with sine squared. If I see 1 minus sine squared, I'm immediately going to replace that with cosine squared. So be sure you review your Pythagorean identities. I believe those are going to be provided on the formula sheet for the exam, but you'll need to recognize and apply them. So that's number 60.